Welcome back to the signal processing for millimeter wave. So, today we will be now moving. So, today we will be covering the things that we will be covering are the following to a MIMO level. So far we have talked about single antenna input, single antenna output system. Now, we will be graduating to the multi antenna system. So, now let us see in the multi antenna system how things go on, how exactly the steering is done and other things, what are the other aspects that will be coming. Now, along with the MIMO, obviously the natural extension will also be MIMO WebDM, right, and then MIMO WebDM, and all things will naturally be appearing it. So, let us graduate to MIMO things and let us see how from a beamforming point of view in millimeter wave, how exactly the MIMO configuration is done. So, we know single antenna single output system. So, when I again repeat the misconception that many people have, when you have a single antenna system, single antenna is not SISO system. SISO meaning single input, single output. What does it mean? It is a single data stream, single output data stream, nothing to do with antenna, right. You can have multiple antenna, just like your beam. I think that part is much more clear. So, now when I say MIMO, beamforming context, in the context of beamforming, MIMO meaning again the same thing, multiple data from the input side, at the same time multiple data at the output side for observation. Okay. So, let us think of it from the transmitter point of view. Let us say what happens when I go for a normal MIMO, forget about beamforming, right. So, you have one data stream here, or say let us say I am just taking 2x2 system or a 2 input system. Okay. So, this is my x1 data. So, this is from a digital side I am creating one set of data, and from digital side I am creating another set of data. So, this is your, and if I have a receiver, suppose this goes to one antenna, this goes to one antenna. If I have a receiver, let us say I have 2 receiver. So, it is a 2x2 system. It is simple. I mean, we have already explained it in the context of 6 gigahertz, sub 6 gigahertz channel model. So, here your channel is a 2x2, straightforward. Okay. Now, you may say that okay, hey, beamforming also we are doing the similar thing, right? Yeah, that but that was from a multi antenna system, not multi data stream system. So, as because here I am pumping the same data with one antenna. So, similarly we may think that okay, number of data, number of antenna remains the same. So, that is something that you need to come out of that notion. So, when I say, so this is the MIMO part. Okay. So, what is the data model of a MIMO part? So, if I say I am receiving y1 n here, I am receiving y2 n here, and what are the different branch street I can think of. So, these are the these are the channel part. Now, here I am talking of a single tap system. So, which means that from one antenna to another antenna it is it is having only one tap, no multiple tap, because moment there is a multiple tap you cannot handle just by a MIMO, rather you have to bring in MIMO WebDM. So, we will talk about the WebDM part in the context of beamforming after we finish the MIMO. So, there I will first talk about what exactly the WebDM thing, then we will talk about MIMO WebDM and what is MIMO WebDM beamforming. So, here we are talking of MIMO beamforming. Okay. So, from the MIMO beamforming point of view, I am completely assuming my tap is a single tap channel. So, which means that from any point of any antenna to any antenna, it is a point to point. If I think of, the number of taps will be just one. So, that means from 1 here, 2 here, this is also 1 here, 2 here. So, from this one to this one, it has only one tap. Let us call it H1. Here it may be H2, here it may be H3, here it may be H4. So, this is just one tap, that is coming into, not multiple taps. It is a FIR filter, but having one tap. Okay. So, that is the configuration I am talking of, easy configuration. Okay. Now, let us see from now I am introducing a beamforming. Now, when it is a beamforming, physically I will have multiple antenna, right. That is the point. Unless you have a multiple antenna, the beamforming cannot happen. Now, the question is that does it mean that these two antenna I will utilize for beamforming in transmit side, or these two antenna should I utilize them for beamforming at the RX side? The answer is no. Because here if you look at, you can't even form a beam. If this is what the configuration, suppose this is a MIMO configuration, does it really form a beam? Suppose instead of 2 antennas at the transmitter side, I have say 100 antennas at the transmitter side and I am feeding 100 datas. Will it form a beam? No, it will never form a beam. I mean, to form a beam, what is the criteria? It is not just multiple antenna. More than that, there has to be a phase aspect coming, right? So, question here is that, suppose I have a multiple antenna. So, there are n antenna, but on each and every antenna I am feeding a different data. So, say I am feeding here S1n, I am feeding here S2n and I am feeding here SNTN, right. So, that is the data I am feeding it. Okay. So, now does it form a beam? The question. And each and every antenna is isotropic antenna. Let us see that. That gives the answer why this is not same as your beam forming case. Okay. So, what happens when this kind of thing? So, let us say a similar concept you just bring in. Let us say I am standing at a position theta and phi. Let us say the distance between them is also d. All things are maintained. Okay. Now, what will happen? The received ER, earlier what we did E0 1 plus e to the power j phi 1 and so on and so forth, you are doing it, right. Right, no? And this one e to the power j phi 2 and all things we are doing it. Now, what was the phi 1 for us? If it is ULA, it was 2 pi by lambda. Do not think about ULA, just generalize it. The position of the antenna where it is. So, let us say it is not exactly 1 or rather the Lth one. This was the vector multiplied by the d vector. D vector was the position vector of this area, this point where I am observing it, right. Now, whatever comes, it will be coming, but now will it be the case? When I am feeding multiple data, will it be the case? Do not be the case. Why? Because apart from the phase difference that each and every antenna is seeing because of their distance, interdistance, and another phase will also appear because I am feeding the data differently. So far if you look at the CISO case, I am feeding the same data. Steering part you keep it apart. We know how to handle steering. Keep the steering part apart. So, earlier if you look at, it is the same data going everywhere, right. So, from the data point of view, every antenna is facing the equal amount of phase, right. So, if this SN here is having a phase, say whatever, something say phi 0, that phi 0 will be seen by every antenna, and hence at the receiver side that phi 0 has no impact. So, what does it mean? It means that when I do the ER, here on the E0 part there will be a common, there will be some common e to the power j phi something will be coming into play, right. So, here if I just draw it, there will be an extra e to the power j phi 0, because for every antenna it is the same data going, but now that is not the case, which means that every point I will see a different phase. In fact, this will also not be 1, it may be something else. So, this phase plus another phase will be coming. It is not phi L, let us put it at Lth data, some put it different symbol phi Ls. Okay. And the worst part is that this is a random variable. This is the worst part. Did you see any random variable on ER? It is a single input, single output system? No. Who is random here? Nobody was random there. E0 was determined by a distance. Each and every phase differences among the antennas was also fixed. Why? Because the distance among the antennas are fixed. So, PL was fixed, D is fixed, So, it is not a random variable. So, that is the reason ER is constant. Constant in the sense that its nature, its phase nature, its plotting nature is constant. But now, along with phi L, I am having a random variable here. Why it is a random variable? Because S1 is a random variable. It is a random variable, obviously. Why? Because that comes from a constellation. So, from time to time, it may be different. Say, I am taking from 16 QAM. This is my data. 16 QAM is my constellation. So, what is the phase of S1 to SNT? I do not know. I know this phase of 16 QAM, but at a particular time, will there be any correlation between phase of S1 and S2 and S3 and so on? Nothing. It just randomly it picks up, right? And the worst part is that, what about the time? So, for example, at n equal to 0, at n equal to 1, at n equal to 2. So, that means individual phase phi L r, whatever I have drawn, that itself is different for every antennas. Across the antennas, that is same at a particular time. Go to the next time, that means I change my sampling time. I go to the next sampling time. This phi r L is again different. That means time to time, this random variable itself is different, and across the antenna that is also different. So, that means it is random in time, in random in space. So, it is a random variable. So, if it is a random variable, what will be the spectrum here? Can I see a nice beam there? I do not know how the phi L r would be there, unless the phi L r is certain, it is a constant, you cannot form any beam. So, you can't even predict how the beam would be, and even if you know this is what the phi L, next time again the beam pattern will be changed. That means, from time to time the patterns of the beam itself is, first of all this itself will not create a beam, because this is a random variable and you do not know how the random variables will be placed, right. It has, if it is a 16 comes, 16 values will be placed there randomly. So, the beam probably, I am just making some drawing. So, beam probably something like that, beam will be. When I go to the n equal to 1, again some other beams can be created. When I go to the n equal to 2, probably a different set of beams may be created. You have no prediction about the beams, and that is the reason when I say MIMO, general MIMO, normal MIMO, it simply means I am sending multiple data to different antennas. Moment it's, though it is a multi-antenna system, they will never form a beam, because to form a beam, I need to precisely control the phase. Now, at every point I am seeing a different phase, and that is random. So, it will never form a beam. Okay. So, this is the first part of our understanding. So, MIMO is not same as multi-antenna beam forming system, they will never form a beam. Okay. Now, let us understand in the context of MIMO, how can I do a beam forming? What is the beam forming concept in the context of MIMO? So, I hope you understand the problem associated with the MIMO system as far as the beam is concerned. So, this is not a beam forming part. Now, let us see how I can extend it to a beam forming part. Okay. Now, let us take a very simple example and try to understand what if this is what we would have done. Let us take a very simple example of two data systems. So, let us say I have S1n data, I have S2n data. Two data I have taken it. Okay. Now, you can think this is some sort of a MIMO system with two input, not two antenna. Okay. Two inputs, so 2 cross something, depends on how many RX I have. Now, let us say this one I individually send it across say anti-phase shifter. So, I have a phase shifter here. Just like you can think of that I have two seesaw system parallelly going on. Okay. Think this way, though it is not the correct way of configuring, but let us assume to start with this is how I am going it. Okay. Similarly, here also I am just putting the way we have done seesaw beamforming. Let us say I am feeding this on a separate antenna. first assume separate antenna, though this is not the configuration, but let us assume from our simplicity or understanding point of view. Okay. So, what I have done? I have two system, two feed line, two data line rather, and that data line. So, this has its own RF analog, everything, this has its own RF analog, but they are two, two separate data line, okay, but in the same IC chip or in the same mobile system, but there are two different data system. Okay. I can create an individual beam here, I can steer it individually, I can also create a beam here, I can also create an individual steering there, there is no problem. Now, if I can ensure that this beam and the beam number 2, they do not interfere with each other with great I would say with the main lobe, great lobe or main lobe, then they do not talk to each other. Okay. So, which means that if this is a simple ULA configuration, let us say with this is the beam, let us not put in a single one, let us put it on a similar line. Okay. Let us say from the first side I get a beam of in this direction, whatever, and from the second side I get another beam like that, main lobes, I am not interested in the side lobe, main lobe. Now, from here this is my theta polar diagram I have drawn. So, this is a one direction, this is another direction. So, this is theta 1 and this is theta 2, positive or negative does not matter, but this is what I have done. I can create that. Okay. Will this system work? Is this a feasible system? Cost wise do not worry, this is not the reality, there will be some more optimization we will do. So, number of antennas will not be the same the way I have drawn, but this is just from a basic understanding. Can I implement this? Will it create any problem? Now, here if you notice it, this is basically a 2 cross 2 system. It is not 2 cross 2, at least the 2 input system. If I say this is a MIMO system, this is the first instances of my multi data transmission in a beamforming manner. So, I have individual point, I create, I just take one data and do a single input single output kind of beamforming, separate them physically, and we have to ensure that both the phases of these two systems are different, in the sense that both the beams they do not they do not overlap. Now, this is a feasible system, okay, there is no point in that. So, that means this, though it needs 2 NT antenna, that is okay, I am not worried about that part first, but at least this is a basic MIMO beamforming aspect. So, which means that when I was drawing this fellow, that multiple antenna I feed it to multiple data I feed it to equal number of antenna, even if the number of antennas are more, they do not form a beam because of this randomness in the phase. But now, will it create a phase? Will it create a beamforming now? Yes. Let this be a random phase here, let there be a random phase here. That is coming from my input side, let it be, because a common phase here, no matter whether it is a random or not, does not change my beam direction. My beam will not be steering, or beam will not create any vibration there, because the steering part totally depends on the steering vector part, and if there is a input phase, let it be random, it does not create any problem. So, which means that this configuration, whatever I have done, that may be the first basic step of my MIMO beamforming. Okay. So, I can create a 2 separate, but one key point here is that this theta 1 and this theta 2 should not overlap with each other, which means what happens, this kind of scenario appears. This may be problematic. Why? Because this is the reason where it has tremendously overlapped. Okay. Because of the overlap, the actual beam will be addition of both of them, because any beam is an addition of both of them, right. So, whether the beams are separated in space or not, suppose I am standing somewhere here, I am standing somewhere here in a direction of theta and phi. Logically, I will receive this and that both, because both are going at the same frequencies, at the same spectrum. Now, for the green card, it will not reach here, because obvious reason, its main direction is different. But logically here, when I say ER, the received electric field will be ER1 plus ER2 from one system plus another system. Now, here it may be almost equal to 0, because that is in a different direction, but logically they will be equal, right. Now, similarly, when I am like a overlapped beam, see if a receiver is sitting somewhere here, I will be receiving ER1 plus ER2 both. Now, because they overlap, they will interfere. So, the effective beam, when I add them up, I do not know whether it will look like a this particular, whether does it look like this, or because of this addition suddenly some extra power may come appear at that side, because they add up, right, and you do not know whether they will add constructively or destructively, you do not know that part. So, something may happen here. You can try it in MATLAB or any other software and try to see if they overlap, what is the what is the ER1 plus ER2. You may see that they do not exactly create a very nice shape, they may distort it, they may get distorted. So, it is advisable that when you have multiple such physical MIMO system, you have to create two separate the separate beams like that. Otherwise, if they overlap, they will destroy the beams each other, they may be creating interference part of it. But in this case, the only problem here is that you need two antenna. So, this is not a physical, this is not how exactly it will be done, but this is only for your understanding part, okay, just for your understanding that I am creating a configuration like that. Okay. So, now this is the first point of the MIMO. So, in a conclusion, for this particular configuration, I need, it is as if like each and every data stream is creating a separate beam for it. Now, if I have you, if I ask you a quiz question, see if I have m number of, suppose I have an antenna system, I have not still talked about the receiver part, what happens there. Well, I am still in the transmitter side. Let us say I have m cross n MIMO system, but I want to do a millimeter wave beamforming. So, what is the first thing that I need to do? First thing is that I will have this is my second so physically this will be the data and they have their own RF and ADC. So, when I say multiple RF, does it mean that RF frequency will be same or different? No, RF frequency is not different, just the RF circuit can be placed differently, because if you have a multiple RF, then there is no point of separating the beams and all, right. Suppose here if you look at, if the RF frequency itself is different for this two stream, suppose this is working at 60 gigahertz and this is working at 70 gigahertz, do I really need to separate them physically from a beam point of view? No, because these two different frequencies, right. If there are two different frequencies, why do I need to separate them? Anyway, they are orthogonal in frequency, right. Okay, so I am assuming that it is not 70 gigahertz, it is still 60 gigahertz, or it will be 70 gigahertz, both the cases. So, RF I am making the same, even if I have multiple data stream, the RF will be same. So, I am not changing any RF frequency. So, here when I say I am having multiple RF, it is only multiple RF circuits, but the frequency of those components would be same. See, if it is at 60 gigahertz, everybody will be 60 gigahertz. Okay. Then what I do? I separate them out. here also I separate them out. How many? Let us say NT. Everybody I put it equal. Here also NT. So, this is the first configuration. So, this part is perfect. So, that means moment I say I am having MIMO system, say M cross N, so M side. So, it is like a M number of such branches I can create it, and I have the potential to create a beam in M different direction, because each and individual point can have their own phase shifter. Can have their own phase shifter. So, these are my phase shifter. It is like a M number of seesaw system, kind of that, okay, and I can create. So, the quiz question is that how many in how many directions I can create my beams. It should be the M. If I have M cross N number of data, I can create M number of direction of my beam. So, when I am having a MIMO, the potential benefit of this MIMO is that, of course, there is a data part, that is a different issue, but from a beam forming point of view is that I can physically create M number of beams in M different direction. Okay. What does it mean? It means that if I see my beam individually, I can steer it. If I see my beam, I can have a beam like this, I can have a beam like this, I can have a beam like that, I can have a beam like this, and so on and so forth. Okay. Probably I put a different color. All different M numbers. So, this is my first beam, this is my second beam, this is my third beam, this is my mth beam. So, I can potentially create M number of beams at different directions. So, that means I have one user here, I can serve him, second user I can serve him, third user I can serve him, and you have mth users you can serve him. Okay. So, using MIMO, potentially I can create M number of beams. As many as beam I create, I can create that many number of data stream I can want. So, with this basic configuration, I end the MIMO beam forming part for this session. In consecutive sessions, we will be talking more about the MIMO beam forming, what are the actual configuration that is taken, how the beams can be created, so and so forth, and what are the RX side, what is the equivalent part the RX side, and what are the data model that I am creating it. Okay. So, those are the things I can discuss it in the next subsequent classes. So, with this I end this class. So, in conclusion, we have kind of completed the and the reference will be same as what we have. Thank you.